Okay, you guys, so hopefully you downloaded these papers, and we're going to start looking at particle motion. It's going to feel very fragmented right now because we have some ideas about particle motion that we did before. Now we're going to add integrals to it. So I just want you to sort of just be thinking, I'm just soaking it in right now. I'm not going to be perfect by the end of this, but I'm going to start putting some things in place. Okay, so what we're looking at is when we talk about a particle moving along either the x-axis or like the y-axis, up and down or left and right. And we will go back and we'll go back and look at one of these graphs that we did before. And we're going to see, okay, where does the integral come in on this? Okay, so let's just look at the real basics. Okay, so there's three things that we're going to be looking at. Saying, okay, let's say that we have a velocity graph. Okay, so let's say that this right here is velocity. And we want to find displacement, total distance traveled, or actual position. Okay, so you might have to think about this because it's been a little while. Like, what the heck is the difference between all of these? So let's say that you have some particle and you go like this, and then it turns around and goes like this, and then it turns around and goes like this. Okay, so where it ended, like this distance from here to here, from where it started to where it ended, that's its displacement. Okay, so how far did you move, not how far did you go. Okay, so think about that. Okay, so that's displacement. We don't care about the initial value. Okay, so initial value will have no effect. Okay, because we just want to know, who cares where you were? How far did you go? Okay, that's going to give me displacement. Now, if I wanted to know total distance traveled, well then I would have to add up this distance from here to here, this distance from here to here. But remember, if velocity is negative, if it's going to the left, so I would take the absolute value of anything going to the left. But I want you to think about total distance traveled, add all of those up. Again, it will not be affected by the initial value. Okay, now, and I'm going to go back over what these mean. Okay, now, if you want actual position, then you're going to take into account the initial value right here. And again, I'm going to show you how that's going to work. Okay, so we have, well, let me see, what do I want to do with these? Okay, let's look at displacement. Okay, so if this is velocity, remember that the area under the velocity curve was position. Okay, and we said if velocity is positive, it's moving to the right. Now the velocity is negative, it's moving to the left, and now it's moving to the right. Okay, so if we want to find the velocity on some interval, we would add a1, subtract a2, add a3. Okay. Now, this is going to be important because eventually we're going to have to look at where are these things negative if we want displacement. Now, if we want total distance traveled, well, we don't need to worry about that negative because we're just going to take the absolute value of that. And if we take the absolute value of it, it'll make all of these guys positive. Okay, now the actual position says, oh, if you want the actual position, the integral will take into account whether it went positive, left, right, and then just add in where you started. Okay, I know that's probably still a little bit not clear. But let's see if we can come up with something to make it more clear. Okay, so let's look at this guy right here. And let's say that they give us this initial condition. So the position is started at 4. And we have to find the displacement, the total distance traveled, and the position on the interval from 0 to 10. Okay, so let's see displacement. So we said, well, displacement has the initial value, we don't care about that. That we should just add anything above, subtract anything below. Okay, so if I want displacement, I'm going to show from 0 to 10 of VT dt equals, so let's see, 18 minus 12. Maybe I'll put it right here. So it equals 6. That's my displacement, okay? And that, I don't maybe necessarily have to show that, but I do have to show this, okay? Now, the next thing we want is total distance traveled. Okay, we said initial value has no effect, but we're going to put in absolute value bars. So from 0 to 10, absolute value of V of t, dt. So we would add these two, 18 plus 12, and we would get 30. Okay, so this is saying that it moved 18 to the right, and then it moved 12 to the left. So it went a total of 30 units. Okay, but if it went 18 to the right and then turned around and went 12 to the left, its displacement, it's 6 places from where it was when it originally started. Okay, now we want the actual position. So we're going to take into account our initial value, which told us that S of 0 was 4. So we're going to go 4 plus 0 to 10 V of t dt, which we just found right up there as 6. So if we were on a number line, we would be at 10 when we get to that spot right there. Okay, so this one is affected by the initial value, and we can see that because it's in the formula. But it seems like sometimes you'll be reading a word problem, and you're not sure if you're supposed to use that initial value or not. So remember, sometimes you might get initial value, and you don't need to use it in these two cases here. Okay, so my goal right now is just that we're just getting familiar with the notation and familiar that area under the curve is the integral. Okay? All right, so let's go back and look at something from way back in the beginning, a velocity graph. And let's see if we can wrap our head around this. Now, the reason that we go kind of into velocity and acceleration and all that is sometimes when we're working with these integrals, it's easier if we have something that we can compare it to. And we could say, oh, it's like you're finding the distance under the velocity curve. It really does give us a nice little, I don't know what I would say, something to compare to. Okay, so all we're going to do here is we're just going to get like some of our thinking back in. Okay, so we have this velocity, and they want to know for what intervals of time is the particle moving to the right. So we have to remember, because we have to justify, it moves to the right if the velocity is greater than 0. Okay, so that's our justification. So I'm going to come over here and I'm going to say, okay, between 1 and 3, it's moving to the right, and between 7 and 8. Okay, so 0 is less than t is less than 3. And 7 is less than t is less than 8. Okay, so that's some old stuff. Okay, what intervals is the particle slowing down? And again, we have to justify our answer. So we're going to say when V of t and A of t have opposite signs. Okay, and I know it's been a little while since we've done this, but remember we made like a little thing here and we said, okay, let's look at velocity. Now, remember that if we're above the x-axis, velocity is positive. When we are below the x-axis, velocity is negative. Okay, let's look at acceleration. Now, remember that acceleration is the slope or the derivative of velocity. Okay, well, in here, that slope is positive. Okay, right here, velocity is constant, or we could say acceleration is 0. Okay, from 2 all the way to 4, that acceleration is negative. Did I do that right? No, it looks like that should have been a negative right there. Let me see if I have some white out. Positive, positive. Oh, no. Never mind. I got it. Don't worry. Okay. Oh, I see. That's where I messed up. Okay, so here acceleration is 0. And now acceleration is the slope, positive. So if they have opposite signs, we know that it's going to slow down. Okay, so I can see opposite signs right here between 2 and 3. I don't know why I put 0 because it's something that I do. And also in here between 6 and 7. Okay, so just kind of getting some of that back in our brain here. Okay, when is the particle stopped and changing directions? Well, it's going to stop if its velocity is equal to 0. And it would change directions if its velocity changes sign. Okay, so we can see when we talk about when the velocity is 0, these are the x-intercepts. And it's just kind of good to think about it that way, because sometimes when you do a bunch of these, you get really used to looking at the graphs and you're like, oh, yeah, this is where it stopped turning, it's turning around. Okay, so we're going to say that it's at t equals 3 and at t equals 7. Okay, it stopped right here, but this is where it was starting from, so it didn't change position. Okay, on what time intervals is the acceleration 0? Okay, so the acceleration is 0 when velocity is constant. Okay, well, we found that right in here, there and there. Okay, so between 1 and 2 and 4 and 7. Okay, so right in there. Oops, that doesn't look like 4 and 7. That looks like 4 and 6, right? Okay, I'm going to stop right now because this video is way too long. Bye-bye.